In example 2, we're given some information about probabilities to do with these two sets A and B. So the first thing that I'm going to do is I'm going to draw a diagram. And in part B, we are actually asked to create a diagram to represent these events. So we've got our sample space, and within this, we've got our categories A, or our sets A and B. Now, what we're asked to do in part A is we're asked to explain why the events A and B are not independent. So remember, if they're independent, then we would have that the probability of A and B happening is the probability of A happening multiplied by the probability of B happening. That's our definition of independence. So in order to show that two events are not independent, we're going to show that if we times the two probabilities together, probability of A times probability of B, we don't get the probability of A and B. So let's write that down. Probability of A times by the probability of B. In this case, it's 0.3 times 0.4, which is 0.12. Now, because 0.12 is not equal to the probability of A and B happening, we know that the events are not independent. So we're just going to write that down. Because probability of A times probability of B is not equal to the probability of A and B happening, we can say that A and B can't be independent. Okay, in part B, we're given another event, C. So we're going to have to draw a circle for C on. And we're told that the events A and C are mutually exclusive. Now remember that mutually exclusive means that they don't overlap. The definition that we used before is that we know that the probability of A and C happening at the same time is 0. So that means that the A circle and the C circle don't have an intersection, they don't overlap. So we know that the C circle is going to be separate to the A circle. But we're not told that it is mutually exclusive to B, so we could have a case where C and B have an overlap, where that intersection's not 0. So we could call that C. Now we're also told that the events B and C are independent. So we'll bear that in mind. Let's just write down what that means. That means that the probability of B and C happening is the probability of B happening times by the probability of C happening. That's a definition of independence. So actually, we can work out what the probability of B and C happening is, because we know the probability of B is 0.4. We were given that at the start of the question. And we know the probability of C is 0.2. So if we times them together, we find out that the probability of B and C happening is 0.08. So let's put that on our Venn diagram. We know that that region there has a probability of 0.08 of happening. So we need to try and fill in the rest of the Venn diagram. I'm going to fill in this intersection first because that's always a good place to start. We know that the intersection of A and B has a probability of 0.25. So we can fill that in. This region here has a probability of 0.25. Now we know the probability of A is 0.3, so we know that the probabilities within the A circle have to add up to 0.3. So I know that this remaining probability, this region here, must have a probability of 0.05 of just A happening and not B happening. And similarly, we can do the probability of C is 0.2, so we know that the probabilities within the C circle add up to 0.2, So we know that this probability of this region must be 0.12. And again, we know that the probabilities within the B circle add up to 0.4. So we can do 0.4, take away 0.08, take away 0.25 to work out this probability as 0.07. And then we filled in each of the separate regions within this Venn diagram. But what we're missing is we're missing the probability outside of the circles, because we know that the sample space has to add up to 1. So if we do 1 subtract each of these probabilities, then we'll work out what probability needs to go on the outside of the circles. So if you work that out, you get 0.43. And that ensures that if you add up all of the probabilities in each of these regions, you get 1. So in part C, we're asked to find this fairly complicated looking probability here. So this is the probability of this event happening. So it's the intersection of A and B dashed combined with the union of C. So let's try and say this in words. So we've got the union of C and this set here. So this set here in the curly bracket, A and not B, we just need to work out what's that region on the Venn diagram. So that region is where the event A happens and B doesn't happen. So that's this region in the Venn diagram. That's where A happens and B doesn't happen. So that has a probability of 0.05. And then we're doing that region union with C. So we could be in this region, or, because remember this means or, we could be in the region within the C circle. And we know the probability of the region within the C circle adds up to 0.2, because we're told the probability of C is 0.2. So all we're going to do is add together those separate regions because they don't overlap. So the probability of being in this region or the C region is 0.05 plus the probability of being in the C region, which is 0.2. And we get that probability as 0.25.